Good morning, everyone. I think it is time to begin with the morning session. We have 4 talks. The first presenter is Andrea Steiner, and she'll talk about advances in using GNSS radio occultation for climate. It is a 20-minute talk, so I would like to remind that in the 17 minutes, there's going to be a sign. And Andrea, whenever you're ready.
Good morning. Now. Good morning. I will present some recent results using GNSS radio occultation for climate and also show some preliminary results today. I would like to thank my colleagues who prepared data, who provided the graphics, Florian Ladstätter, Matthias Stocker, Marc Schwerz, Camilla Jesimbet, and Katrin Raj of the Wegener Center for Climate Change in Graz. So our troposphere and stratosphere, including the tropopause region, shows large variability in space and time. We have relatively small vertical scales, small to large scale waves, and scales from diurnal to interannual time scales, and also decadal changes. And GNSS radio occultation provides atmospheric observation for observing this variability and changes, and for analyzing these changes due to the high vertical resolution, global coverage, and specifically long-term stability for climate analysis. Recently, we experience ever more extremes, including wildfires, including large wildfires. These large wildfires have aerosol emissions that are comparable to moderate volcanic eruptions. Examples are the North American wildfire in 2017, the Australian wildfire in 2019 and 2020, and these large aerosol injections have also impacts not only in the troposphere, to the surface, but also up into the stratosphere. And this is what you see in these temperature anomalies on the top right plot, collocated anomalies with the aerosol plume, where you see this stratospheric warming after a few weeks. And also at the bottom, zonal temperature anomalies months before the wildfire and then after the wildfire, showing a warming in the stratosphere. And for example, the Australian wildfire caused a warming of the stratosphere that was larger than any signal from recent volcanic eruptions. And this maximum warming that we saw here was more than 3K, lasted several months in the stratosphere. Now, when we compare to volcanic eruptions since 2002, we had moderate volcanic eruptions, which also injected volcanic aerosols into the lower stratosphere. You see here this aerosol load in the top right plot, altitude over time, and the corresponding temperature signals due to these aerosols from the volcanic eruptions. You see here warming for each of these volcanic eruptions in the lowermost stratosphere, and also a cooling due to the upwelling of ozone-poor air above. Overall, in the tropical mean, this means about 0.5 Kelvin increase in lower stratospheric temperature for these eruptions over a few months. In 2022, we had a very interesting volcanic eruption, the Hunger eruption. The Hunger volcano in the southern Pacific erupted in January 2022. It ejected aerosols into the stratosphere, but what was very extraordinary was the large amount of water vapor that was injected up to 50 kilometers and above. Yeah? And we see here what we did then. We investigated what was the impact of these volcanic eruptions on the stratosphere. You see here two radio occultation bending angle profiles co-located immediately with the plume. But what happened after the eruption? And I again cannot move forward here. Thank you. Yeah, on the left-hand plot, you see the aerosol plume in the atmosphere at around 24 kilometers after the eruption, and you see that it settled downward due to gravitational sedimentation. On the right-hand plot, you see the water vapor anomalies, which moved upward, the water vapor, due to atmospheric circulation. And what we did is a multiple regression analysis. So you will see we get separated the background variability. So you only see here the temperature residual anomalies, which show a strong persistent radiative cooling of up to 4 Kelvin in the tropical and subtropical middle stratosphere until mid-2023. And this clearly corresponds to the water vapor distribution. So we had a cooling over 1.5 years from this volcano. And if you want to know more about it, there is a poster 24A by Matthias Stocker. We also have a paper recently published in Nature's Communication, Earth and Environment, which was even featured last week by the journal. Now, moving from the tropics to the high latitudes. Can you move forward one slide? Thank you. We also investigated the variability at high latitudes. We investigated southern stratospheric warmings. And what we found was different, and their connection to atmospheric blocking. And we found different types here. In winter 2028, as an example, you have a polar vortex that is displaced, resulting in a short-term stratospheric warming, a zonal wind reversal, together with a downward propagation of wave activity. So we also computed the EP flux here. And then subsequently, we have a blocking formation in the North Pacific region. Another type of these SSWs was in 2019. Could you move forward my slide, please? One back. Come on. And in 2019, we had an event where the vortex split. So you have a longer southern stratospheric warming, a prolonged zonal wind reversal, and wave absorption with a subsequent formation of blocking in the Euro-Atlantic. So these different types of southern stratospheric warming result either in blocking in the North Pacific or in blocking over the Euro-Atlantic. So why is this important? Because for example, blocking over the Atlantic in winter and spring is also connected or can trigger cold extremes over Europe or for Europe. For example, in 2016, we had then the spring frost events in southeastern Europe, damaging our crops. In summer over Europe, if you have this blocking situation, this can trigger hot extremes and prolonged heat waves. And can you move my slide forward? Thank you. And understanding extremes, understanding long-term changes is on the agenda of the World Climate Research Program. In their core projects, in their new lighthouse activities, for example, on analysis and prediction of Earth system variability and change, with contributions to IPCC assessments, to the agenda for sustainable development. And within this World Climate Research Program, the activity on atmospheric temperatures changes specifically works on understanding atmospheric observational records, including radio occultation and assessments of atmospheric temperature trends and attribution of atmospheric temperature trends. I don't know what I do wrong here, but it just doesn't move.
I can move them for you.
Yeah, next slide, please. Thank you. So the IPCC already stated that radio occultation is a new observation technique, permits more robust quantification of atmospheric temperature changes. And I will show now some new or some preliminary plots on atmospheric temperature changes based on, next slide, based on atmospheric temperature observations, including layer average temperatures from southern stratospheric sounding, from the stratospheric sounding unit, from the microwave sounding units, and also from vertically resolved temperature records, including radiosondes, including GNSS radio occultation, and also data from the microwave limb sounder. So here you see stratospheric temperature trends from 1979 to 2023. This time series of the different channels of the instruments. At the bottom, you see the temperature of the lower stratosphere here, then the SSU channel 1, 2, up to SSU channel 3 for the upper stratosphere. Overall, we find trends or a decrease in temperature, stratospheric cooling of about 0.2 Kelvin in the lower most stratosphere, up to 0.7 Kelvin per decade in the upper stratosphere. So we have this increase of magnitude with height. You also see the impact of the large volcanoes in the 1980s and 90s, El Chichón and Pinatubo, and you even see this impact of the stratospheric warming by the Australian wildfire. If you look carefully at the very end of this, in 2023, you can see a slight cooling here, and then an increase back to normal again. This might be this impact of the Hunger volcano that we see here. Next slide. When we resolve the trends latitudinally, we see a consistent cooling in all these layers over all latitudes with a bit higher uncertainty at higher latitudes. Next slide. Regarding the troposphere, we have here the lower troposphere channel of the MSU time series and the middle troposphere channel corrected for the stratospheric contribution. Overall, we find a warming of about 0.2, 0.15 Kelvin here in the troposphere from this observational data. And when we look at the latitudinal resolved trends, we see this large warming trend in the high northern latitudes.
Apologies, could you move a little closer to the podium? Yes, thank you.
Yes, thank you. Now, when we look at the vertically resolved trends, we included here radiosondes together with this layer average temperatures. We see quite good consistency, a warming of the troposphere, significant warming of the troposphere, cooling in the stratosphere for the time series 1997 to 2023 for the global mean in the left, for the tropics on the right. Next slide. We also tried to include ERA 5, which doesn't perform that well in the stratosphere. And when we include radio occultation data, next slide, we do this for the time period 2002 to 2023. You see here in blue radio occultation data based on the ROMSAF radio occultation profiles. We find quite good consistency with the radiosonde data, a warming again in the troposphere, specifically strong warming in the tropical troposphere of about 0.2 to 0.4 Kelvin per decade, and also a warming near the tropopause and the lowermost stratosphere. Next slide. This is the inclusion of ERA 5, which shows consistent trends in the troposphere and near the SSU levels in the stratosphere. Next slide. This is also, in addition, data from the microwave limb sounder since 2005. So this is the trend for 2005 to 2023. It also shows overall quite good consistency here in observational trends with some differences which we have to investigate further. Next slide. Now the height latitude resolved trends of temperature from 2002 to 2021 are shown here for our new Wegener Center record, the ROPS version 1.1 on the left-hand side. And you see here that tropospheric warming, stratospheric cooling, this strong warming in the tropical UTLS and the Southern Hemisphere extratropics, and very good consistency with the ROPP climate record for dry temperature. Next slide. And also the physical temperature is shown here, the trend on the left-hand side for the Wegener Center ROPS version 1.1, which is also quite consistent with trends in radiosonde data. So you see here that the radiosondes are sparse in the tropics and in the southern hemisphere. So overall, this tropospheric warming, stratospheric cooling also causes a change in the tropopause. Next slide. Not quite yet, but you see this changes now in these map plots. I'm almost done with the warming of the upper troposphere, the cooling of the stratosphere, and this hemispheric asymmetry in the lowermost stratosphere. And we will hear a presentation by Ioden today on this topic. And now my last slide on the change in the troposphere, so preliminary results. Next slide, please. That show the lapse rate tropopause height on the top left, the lapse rate tropopause temperature trend at the bottom, and you see here an increase in tropopause temperature in the tropics, a decrease at mid to high latitudes, both significant, and a corresponding increase of lapse rate altitude, but nearly no significant trend in the tropics. Now, if we look at the seasonal trends, which you see here on the right-hand plots, for boreal winter in blue, for boreal summer in red, you see that in the tropics you have in DJF a decrease in altitude, in lapse rate tropopause altitude in summer, a bit of an increase. So overall in the annual mean, you do not see this trend here. So as said, this is preliminary results, and what we think as a community, what is important now for us as a community in using radio occultation data for investigating the atmosphere, for investigating the climate, is that we should prepare for the next IPCC report and the challenges ahead. We should focus on the production, the publication of new reprocessed radio occultation climate data records, their validation, including measurements from recent remissions. We should focus on the provision of climate variables, climate indicators, and contribute to a better understanding of Earth's changing climate, from atmospheric processes to atmospheric trends to the impact of extremes. Thank you for your attention.
Thank you very much, Andrea. That was an excellent talk. We have time for a quick question.
Oh, now comes a hard one.
No, Andrea, that was really nice talking. There's been a lot of work in our community for a long time looking at the temperature record from RO with other sounders. I think the frontier is an additional frontier is the water vapor or
Yes.
the lower tropospheric. And there's a lot of information that hasn't really been used. And it's a challenge to our young people or older people even to think about the water vapor information. The record is long enough to think about climate variability. So
Yeah. I
Just a
totally agree, and it is a recommendation of the IROWG also to exploit water vapor.
Andrea, I think this is a very good summary and also lay out the challenging ahead. And interesting enough, because now we are actually talking about not only RO, but also some other combined observation from, let's say, MLS and others. And these two are actually totally two different things. So I think that the information is really mixing, and it's very difficult to really interpret what is really from what. Okay, but I think your result actually using something. I keep on wondering how we can actually using wet profile for temperature, for example, from 5 to either 10. And can you say something about that? How much information actually at that region? It's actually very complicated because it's a 1dVAR things and it's
Yes.
water vapor is pumping.
Yes.
So the information itself actually drifting according to not only the background, but also the water vapor itself.
Well, the information might be a bit different for different processing, depending on how you do the processing and how much you allow with when you do a 1dVAR, on how much information you allow to propagate with your depending on your covariance matrices. Overall, this was really a first check on how our temperature looks how the physical temperature looks compared to radiosondes, for example, in our new Wegener Center record. And of course, more comparisons have to be made there. Yeah. But yeah, just a notice. I mean, regarding like these trend studies, we definitely will focus more on the tri temperature. So really on the observations, and not to mix too much background information.
Thank you, Andrea.
Thank you.
I would like to invite Julia Dancer.